My name is Robert Chyla. I'm with MIPS, and Jay was with me from NXP. We were pushing the spec. Do you have the clicker?
Oh, it's on the table.
Oh, here. So it's only 20 minutes for a lot of work over 4 years. So I will be brief, and also we put a bit more slides than we can talk about. So just we'll be skipping through all of it, and just quick agenda. What is actually ratified? What are the components? Some overview of formats and compression techniques, and then some reference code for you to look at, and some compression results and some future work which you discuss. For anybody, there's a links into different places, so you can go ahead and read that later. So maybe you can go now.
Hello?
I need to give up.
Hello? OK. To create a complete end-to-end trace solution, we had to ratify 3 separate specs. The first one is the actual N-Trace spec. It is based on the existing Nexus IEEE open standard, which has been available and in use in the automotive industry for over 20 years. Since the original spec allows implementers much flexibility, we decided to reduce the scope and standardize some aspects of it, such as we defined it a bite-sized container for trace egress. The Nexus doc defines the trace messages, formats, and the conditions in which they are generated. It defines a basic set of features which must be supported, and many optional ones that may be enabled by software to add better trace compression. A N-Trace reference C encoder and decoder for development and verification can be found in our GitHub repository. The second document to be ratified is the trace control spec. This documentation provides the register definition for each component that can make up a trace ecosystem. Since this document is shared with eTrace, there will be some registers or bits which do not apply to the N-Trace-based system, and the details of what's supported can be found in the N-Trace document itself. The last document is the trace connector spec. It defines how the data signals are connected via a MIPI 20 or MICTR 38-bit debug and trace connectors, industry standard connectors that are used widely by tool vendors. Next slide. Now let's focus on what the trace control spec defines before we actually dive into the actual N-Trace spec. Like I said, this is shared or can be shared with eTrace or other debug infrastructures. The control spec defines a register definition of the following components. The trace encoder, which is usually highly coupled to each heart and generates the actual N-Trace messages. The trace funnel combines trace from several encoders or other funnels. The trace PIB sync sends the trace data to the actual SoC pins. This module has multiple different configurations. It can support parallel from 1 to 16 bits of data or even serial transport. And also there is a trace RAM sync, which allows a trace to be saved locally to a small buffer or some type of RAM, or actually to the system-wide RAM buffer. Each trace component occupies a 4 kilobyte address range. There is currently no auto-discovery support, so the base address of each component must be known and passed along to the debugger or the host debug tool by a config file. Each component also has an active bit in the control register, which allows for clock gating of the component for power savings. All right, next one. All right, so this is basically kind of a high-level diagram of what a trace infrastructure will be, right? And so I'm going to kind of go through the steps of how you would do it. So the first thing you do is you actually program the components before you actually start trace, right? So you can program the components through either the debug module that has access to some type of debug interconnect interface, or an actual host processor can actually run this as well. So you can program all the encoders and all the other downstream components. So the heart will be running, generating trace messages, sending the information to the encoder. And in this case, we have 1 encoder per heart. And so each encoder will introduce data to the funnel. So the funnel will arbitrate between which data, which packet is processing, which encoder is processing, and send that downstream. Now, the funnel can be lightweight as well. It's defined where you actually don't have to store an actual whole packet or whole information. You can just have it really light and nimble and just feed stuff in, feed the data through without actually storing it. That's one nice thing about Nexus allows you to do. You can actually see when the start or end of a packet is in the trace stream, so you don't have to actually store all the data. And so typically what you do is you will sync to some type of sync source, right? So the first one on the top is you could be to the SRAM. So this would be to a local buffer that was just dedicated for trace. And in the definition, you'll have the read and write pointer registers and how to access that as well from the outside world. And then, of course, you have the PIB sync, which is basically how to get this stuff egress off chip to the actual tools that you'll see. You could also have an ATB bridge, which allows you to interface with other type of ISAs or other type of debug infrastructures using the standard ATB bus going out. And then, of course, you can write to a SMAM sync, which you can store to either system memory or even offload this to a PCI Express to get off chip as well. Now, when you stand back and look at this, this is kind of like the starting building blocks of what kind of core site, ARM core site tools or ARM core site IPs can kind of create. All the trace infrastructure from generating the trace to storing it and getting it off chip.
Right, so talking about a little bit about the N-Trace itself. So there are some basic principles, and these principles are very generic, apply to many traces, including E-Trace as well. First, the ingress port, which is actually part of the E-Trace specification, is sending you a blocks of instructions. So whatever is retired, you see a block. If you have a CPU core which retires many instructions at once, you have just 1 and 10 instructions executed. So that's an input. And on this input, what the encoder does, it counts instructions. And then the second thing it does, it is actually acting to branches. So every branch, it records if it was taken or not taken, taken, not taken. And if you look at it, you're at the point A in the program, and you keep going, like say 5 instructions, or maybe 100, let's assume 100 instructions, and then in the middle you see, oh, there's a branch, and you look, should I take it or not, and you sort of follow the code. That's how it's done. So it's a very simple concept. Just count instructions and mark flow changes. Of course, there are sometimes unknown flow changes. You can't look where they go, like indirect jumps or returns or exceptions. And then you have to stop what you do and drop an address. That's it. So if there's any flow change which you can deduct from a program, you just sort of do nothing. You just count. When is it flow change where the program is actually changing a flow in a way you can't find out by looking at the code, then you have to drop an address. An address is dropped in a different forms. Normally, you drop it only XOR, which is like a short distance. It's a small number, so it takes less space. And also, just to make sure the decoder can act from the middle of the trace, because sometimes you have 1 gigabyte of the trace, you just can't afford like decoding from the very beginning to an end. So you periodically, there's like a full drop of everything. So you drop an address, and you start decoding from there. So decoder can take any piece of trace in the middle, and then it can synchronize. So that's it. And decoder does it the other way. It just follows the code. The sort of wrong thing is that you have to have the code which is traced. And if the code is self-tracing you, there's also a problem. That's a known problem to humanity. So really, you're looking at the code, you follow the code, you count instructions, you do the branches left or right, and then periodically you forward to an address which is reported by the trace. So that's simple. And at the end, there's also every message in N-Trace can have a timestamp, optionally, where you timestamp the event. The question you may have is, because the program flows, right, the timestamp can be sporadic, right? So that's it. But for example, exceptions and everything what changes the modes has a timestamp anyway. So you see the exact timing of interrupts and exceptions, all the important events. It's a brief overview of format of messages. All the messages are sequence of bytes, same, I think, as E-Trace. So each has the type, and I don't really go through this one too much. It's just a sequence of bytes, And these bytes have fields. Some of these fields are fixed size. They're always at the beginning, and some of them are variable size. They are always at the end. And the timestamp, it's the very last one. So maybe completely skipped, and nobody should cry about it. I don't see the timestamp, OK. There's also an option, probably to not emit the timestamp. It's like too much of a, bandwidth taken. You may suppress sending timestamp. It's better than dropping the trace altogether. As a table taken from a PDF which describes the N-Trace messages, how many messages we have. And the T-code field is actually 6-bit, so we only use a few of these messages because that's coming from Nexus. Kind of a bit of a waste space, but from other angle, you have a room to grow, like other event trace messages or some data messages or something else as well. And the fields are always following. I don't want to go too deep into here. You can sort of try to digest it yourself. There are some, compression techniques. First, you have to filter out the boring code. Like code which always runs, doesn't do the harm, you kind of don't have to trace it, right? Memory copy or this kind of stuff. The other compression techniques which we can utilize is you can maintain the call stack. It means every time you call, you push a return address, and then when you experience return instruction, normally return is indirect address. You don't know where it's returning by looking at the code. But because you saw the call, you can skip the return because when it's coming properly. If the return is improper, so the address don't match, you just drop an address, and the decoder should continue from there. But if you don't drop an address, consider the return as a normal instruction, just count it, count it, count it. So that's why what somebody said before, right? You may have on a different meeting, if you have only calls, only returns, it's really like only counts. You just count them, and that's it. The other feature, the third one, is that RISC-V unfortunately doesn't have very far calls and returns, so we have to take advantage of it. If the code is, calculating an address, we can consider this as a fixed address. Repeated sequence of branches, that's also very, very good compression, a lot of data. You have memory copy, string copy, or some code which runs all over the place. And even with ifs, which does the same thing, you can compress that just counting how many times you got the same stuff. Instead of putting in millions of bits, you put one bit, say, million times, right? Which is less bounds. And the last compression is we don't have to send the MSB FFs on the Linux. The Linux code has a lot of running in the FF space, so you want to skip that. Let me move on. There's a reference code. I just really want to say that it's there. I don't want to do too much. Through that reference code, you can actually simulate the trace. All it's needed is a sequence of PCs. So you have a simulator. You can dump all the simulators in the world usually provide the PC sequences. So you put the PC sequence, you can run it through that reference decoder and create a trace. You can see how well it compresses or not, and that's probably the next slide. Right. So this slide is kind of busy. I'm not sure if you can read it. I can't. This is so right. This is the pointer. Oh, there's the pointer. OK. So in here, we have many benchmarks. There are like two standard ones, mbench, set, and then some other tiny programs like rsort, qsort, Towers of Hanoi, like more academic piece of code. So we run through this and calculated how many instructions each benchmark has. And this column is actually what we call branch trace messaging. It's a smaller. Every branch you send, instead of bit, you send a message. Branch happened or branch didn't happen. So that's not suggested way. As you see, this is the HTM where you send history trace message. Every branch creates a bit. And you see already, like from 1.2 bits, right, per instruction, you have 0.3. So 200, 300, whatever, 3 times better compression, basically. And you see the different programs kind of behave differently. Depends on it. And if you go here, this is with repeat, so that's detection of the repeated branches. And some of them are like not so great. Oh, I can see it here. Okay. but I have to point here. So most of these are not, much better. They're at around 0, but this guy, for example, it's like super good because this is CSCR32. And CSCR32 just runs the loop like brute force, and the loop runs always the same, so you can almost completely skip it. That's why this one is excluded from any statistics, because it will just make it wrong. So, and last one is adding the return stack. So in here, we are getting more gain. In here, we have only 7% on average. Some of them are more, but some average is not great. But in here, we have 78% if you add return stack. Because if you don't, and the program is very call intensive, then every return you must send an address. Short address still, but an address. And that's very well visible in this section where for example, Drystone, which is call intensive, got very well improved. The Cormark, which is not call intensive, got no improvement. So this was done through that reference call, and the bandwidth, the average is 0.2 bits per instruction, which I sort of calculated. If you have, say, 1 gigahertz core, right, and 1 instruction per cycles, it will give you 25 megabits per second trace bandwidth, and et cetera, et cetera. So you can, for example, on the Mictor connector, you can trace up to 25 hertz, assuming 0.2, right? And maybe better, maybe worse. So let me then continue. So last topic I would like to address is the future work. And actually, on Monday, there was a meeting. We discussed this. We discussed this also before. I can go to the back slide if there's any compression questions, but let me finish first, and then we see. So first is what we actually discussed. This is from the end of PDF. Instrumentation trace. Sometimes you want to instrument code a little bit to give a focus and maybe some data, and also timing information. And if somebody was at the E-trace, event trace, that's similar thing, some extra data with extra timing, extra information, right? So that's what I call selective data trace, is where we want to, it's comparing to ITM from ARM. You may send some data out of your application to a trace buffer. Just use it as a sort of UART kind of style. You can do a little bit. Full data trace is actually very intense. Nobody sane will do it, because especially on an out-of-order course, you even can't do it. Because you have data transfer, you have no idea from where they are coming. So the full data trace is not a big focus for us to move over. Event trace, that's what was actually donated by Sci5 not so long ago, and Karsten had a talk about it. So only interesting events you trace, interrupts, system calls, this kind of stuff with timing information. And system bus trace, that's also something which is interested on the multi-core systems. You usually don't care how the code runs. You care about interactions on the bus, who is, or something strange event. And then also more compression techniques we can explore to get better bandwidth. For example, if you notice some fields are, because they're strictly Nexus standard compliant, we can squeeze them a little bit and get a little bit of the gain. So that's about it.
Yeah, that's about it. I just wanted to say our main focus will be instrument trace. We're going to try to do that next, add support for that, and then these other ones will follow soon after, hopefully. So
one thing about the title, because title said ratified extension, it's not technically ratified. We submitted the talk 3 months ago. It's only one more signature. Actually, RVA-B and RVA-A get in front of us to the vote, so because they were important, right?
Yeah, and it's close. And I also want to say there's other people that helped us do this. Robert did a great job lifting it, leading the group. But if you look at the documentation, there's other acknowledgments there for the tool vendors and other folks in the community that helped. So we don't have a slide for that, but they're in there, and we want to thank you guys all as well.
Yeah, thank you very much.
Thank you, guys.